Hey everybody, we're back with another week of materials. We're going to be wrapping up our first part of hypothesis testing, where we're going to be looking at the T-test today. We'll do a bit of review as well. We're going to look at p-values, which is another way of looking at the results of a hypothesis test. And that should just about do it. So let's get rocking. So, a little bit of review from last week, and then we'll talk about the p-values, and then we'll look at t-tests. So, here we go. So, review of last week. So, if alpha equals 5% or 0.05, the critical value from the z-tables backwards corresponds to the 5th percentile. So, for a left-tail test, we're going to be looking at negative Z alpha. If you go look that up on your Z table, reverse looking it up, so looking for 0.05, you are going to get a Z alpha rejection of negative 1.645. So in this region, we accept the HO. In this region here that's colored in green, we reject HO. And this is sort of the logic that we have that you want to write down in the test is reject HO if Z is less than or equal to negative Z alpha. If we're doing a right-tailed test, same thing. If alpha is 5%, then the critical value, looking up 95% on the Z table, because we'll have 95% here. Again, this region, accept HO. This region is the reject HO region. So if you look it up on the Z table, you're going to get positive 1.645. So you'll reject HO if your calculated Z statistic is greater than or equal to Z alpha. If you have a two-tailed test, then for an alpha value, again, of 0.05 or 5%, you need to split it up into 2. So we calculate alpha divided by 2 on the right and alpha divided by 2 on the left. Remember that critical values will be symmetrical. So when you go ahead and look up that Z alpha divided by 2, so you'll be looking up 0.025 in this case. You can look it up on the left-hand side, for example, where you're looking up 0.025. And remember, on the left-hand side, it'll be negative. On the right-hand side, it's going to be positive. All right. So let's go ahead and take a look at our p-values now. So p-value is just another way to figure out if you're going to be rejecting or accepting your HO. Now, the reason we talk about it is mostly because in the real world, when you're probably using software for stuff like this, most programs will actually give you a p-value. So you won't usually be looking at tables too often in the real world, although you certainly can. So the p-value is the probability of observing a test statistic. So observing a test statistic under the assumption. So under the assumption that HO is true and it is found from the tables. A small p-value implies that the sample mean is unlikely if HO is true and becomes evidence to reject HO. Okay, so what we've been doing is, I guess, called the classical approach. So if the Z-score that you calculate, right, from the sample collected, if it's too many standard deviations away from the hypothesized parameter HO, then you can reject HO. So what a p-value is it's a percentage, and if it's small enough, and we'll talk about what that threshold is, but if it's small enough, then that is evidence that, again, we can reject HO. So if the p-value is less than or equal to the alpha value, we reject HO. Oops, missed my C. I'm going to try that again. There. So therefore, if the p-value is greater than the alpha value, then we accept HO. The p-value is found from the tables, and most statistical analysis programs will actually return a p-value. So that I already said. So instead of looking for a critical value at a preset alpha value from the tables, we look up the probability above or below the observed z-score. So this is actually how you find the p-score, or the p-value rather. So you actually calculate your Z statistic as you normally do from the sample, and then we go look up what is the area to the left or to the right, depending on whether we're doing a left-tail or a right-tail test. You're going to look up what is the area under the curve, and that is generally the p-value. Let's talk a little bit more specifics here. So for how to compute the p-value for a left-tail test. So for a left-tail test, the p-value is the area to the, you guessed it, to the left of the calculated value, which is the z-score you calculate. So you'll be looking for the probability that z is less than the test value, and that's equal to the p-value. So for example, let's say that you find, a z-score. So you do your work, you find a z-score of negative 1.92, and you're doing a left-tail test, so you're looking for the probability that z is less than negative 1.92. Now go look that up on the table, and you're going to get 0.0274. Go ahead, pause the video, check it out. Now, what this means for us, in this particular case, is let's say the alpha value was 5%. So if the p-value is less than the alpha value, then we can reject HO in this case. So in this case, we have a p-value of 0.0274, and our alpha value is 5%. So remember, you got to turn it into a decimal. Now, is this p-value? Is it less than this or greater than this number? Well, it's less than. So in this case, we could reject the HO. Let's take a look at a right-tailed test. So for a right-tailed test, the p-value is the area to the right of the calculated value. Very, very similar to before. So because it's right tail, you're going to be looking for probability that whatever z-score you get is greater than the test value, and that's equal to the p-value. So if you get a z value of 1.41, you'd go look that up on your table. Okay, so you'd be looking for the area to the right. Now remember, our tables give the area to the left, so you'd have to go 1 minus whatever area you look up at 1.41, so that's 0.9207. You can go ahead, check it out on your table. So here we go. Right there, that would be the p-value. So if the alpha value was 5%, something like that, you would reject if the p-value is less than the alpha value. Now in this case, the p-value is almost 8%, so we would not be able to reject HO. Now we will do some actual examples. Computing p-value for the two-tailed z-test. So for the two-tailed test, the p-value is twice the area to the right or left of the calculated value. So for example, if you have a negative test statistic, basically a left-tailed test, right? Then you're going to go 2 times the probability that z is less than whatever that test value is, and that's your p-value. For a positive test statistic, it's virtually the same. It's just 2 times probability that z is greater than that test value, right? You're going to have to go 1 minus whatever probability you find for z less than whatever that value is, right? Just like on the last slide, and that's your p-value. So here's a left-tail example. Let's say you get z equal negative 2.27. Then you're going to go 2 times the probability that z is less than that value. You'll go look it up on the table. You should get this 0.0116, and you go 2 times that, and there you go. There's your p-value. Now, if it's a right-tailed test, you're going to have to go look up the probability that z is greater than 2.27, and you're going to go 2 times 1 minus whatever value you find when you look up probability that z is less than 2.27, right? You're going to get the same value as before, and there's your p-value. Perfect. So what we have now is I'm going to do an example from last week, and we did an example that was either the same one, same data, but looking at the Righttail version of it. Okay, so company has a new 100-liter trash bag. It's thinner and requires less plastic than their current 100-liter trash bag. So they test 40 of the new bags, and they find that the breaking load is 25.575 kilograms, with a standard deviation of 1.6 kilograms. At the 5% level, can the company make the claim that their new trash bag is stronger than the old one, which has a breaking load of 25 kilograms? So what we're going to do is, first we're going to do this the regular way, then we'll look at it using a p-value. So most of the steps stay the same here. Whoops. So you got to state your null and alternative hypotheses. So we're looking to see if the alternative hypothesis, right, we got a higher breaking load, so it's going to be mu greater than 25 because that's the status quo, and then HO is that mu is less than or equal to 25. No, that stays the same. Then you specify the level of significance, so alpha equals 0.05, and you're going to determine your rejection rule. Okay, so we're going to be looking up Z at 0.05. Now this is a right-tail test, right? So we're going to be looking to reject over here, reject HO, and if we're looking up 0.05 for our alpha value, that means we're going to have 95% of the curve over here. So we'll be looking up 0.95. Now let's go to our Z table. So looking up 0.95, or as close as we can get. Yes, here we are. So we have 0.9495 and 0.9505, right? So you guys should be familiar with this value, 1.6, and then we're in between 4 and 5, so 1.645. Today I'll show you on the t-tables how you can find those values as well. So 1.645. So we're going to reject HO if Z is greater than 1.645. Here's our work. Right now, we did this question last time, so here's us calculating the Z statistic using central limit theorem, plugging in all the numbers, so the new breaking load that was found in the experiment, the status quo, standard deviation divided by how many trials were done, and we get a value of 2.2. Okay, so again, if Z is greater than Z alpha, then we're going to reject HO. So in this case, Z is 2.2, and that's greater than 1.645, so therefore we reject HO, that mu is less than or equal to 25, in favor of HA, that mu must be greater than 25 at the 0.05 significance level. Okay, you must say that, and then the last step is write it in managerial terms, or in English, right? So conclude that the mean breaking strength of the new bag exceeds 25 kilograms. Be careful how you word it. We can't actually say that the breaking strength is 25 point, whatever they found, whatever is 575 or something. All we can say is that based on this data and this alpha value, the breaking load exceeds 25. Very important. Okay, so that's how we did this last week. Now, what if we do the same question, but we're going to use the p-value method? So for the p-value method, we're going to do everything the same up to about step 4, right? So decide whether to reject HO using the p-value. So that means that we need to find the area to the right of the z-score. So our z-score was 2.2. So we need to go look up we're going to go 1 minus whatever value we find when we go look up probability that z is less than 2.2. So let's go to our table here and look up 2.20, so 0.9861. And we can write 0.9861. Now we'll go 1 minus that value, and you're going to get 0.0139. Now, is this less than the z alpha value that we looked, now we get 0.0139. Now this is less than alpha value of, this should say 0.05, because that was the alpha value in the question. So since this number is less than the alpha value, we therefore reject HO and accept HA. And then interpret the statistical results, so we can still say that the mean breaking strength of the new bags exceeds 25 kilograms. So that's how you use p-values. You'd probably get a question on that somewhere on the test or midterm or exam. Now we're going to look at t-test. So what's the t-test? Well, we have our z-test that we looked at last time, but I mentioned last time that what if we don't know the population standard deviation, or what if we have like a small sample? Well, that's what the t-test is for. So suppose the population being sampled is normally distributed. The population standard deviation S is unknown. If the population standard deviation S is unknown, then it will have to be estimated from the sample standard deviation S. Under these two conditions, we have to use the t-distribution to test the hypothesis. So what does the t-distribution look like? Well, I'm pretty bad at drawing, but this one here, right down here actually, so when n is smaller than 30, the t-distribution isn't, it's kind of more like a hump. It's kind of how I draw mine. I try to draw mine like this. When you're close to 30, you're pretty close to being normal, but your z-score distribution actually sort of looks like the blue one. So just a little bit of mumbo jumbo in the background here. So let x bar be the mean, okay, of a sample of size n with a standard deviation s. Mu o is the claimed value of the population mean, okay, and we define our new test statistic as such. So it's a t, and it's equal to x bar minus mu o divided by the sample standard deviation. So we use s and not sigma, and then divided by the square root of n. So central limit theorem is still there. If the population being sampled is normal, and if S is used to estimate the actual standard deviation, then the sampling distribution of the t-statistic is a t-distribution, and we have this thing called n-1 degrees of freedom. This is a correction factor. You know how statisticians love their correction factors. So because we realize that we're sort of not using ideal numbers here, so the central limit theorem really helps, but we also just decrease our sample size by 1, because it makes it that much harder to accidentally reject HO when we shouldn't be rejecting it. So we also use a brand new table because the t-distribution looks different. So we use our t-table. Now the t-table that we have in our class, again, they're all different, but our t-table actually gives the value to the right of the score you're looking up. Doesn't really end up mattering too much for what we do. But if you're doing a Lefttail test, because the values to the right are going to be positive, to find the value on our table, we have to use the negative version of whatever number we look up. So what's the procedure? First, you're going to look up the degrees of freedom, sometimes called DF, and it's always n-1, so your sample size minus 1. Along the top of your table, you can find the appropriate alpha value, so these tables are set up a little different. And then you're going to look where the row and the column intersect, and that's your critical value. If you can't find the degrees of freedom that you're looking for, use the closest one that you can find. So let me just show you the table here. So here's the T-table. Now, over here, you have your degrees of freedom. So starting on 1, and at a certain point, it starts jumping up. So we basically got 1 to 30, right? And then 40, 60, 120, and then infinity, which we'll talk about in a second here. Along the top, you got your alpha values. Okay, and you'll see that the table gives the alpha value to the right. So there's no negative numbers on this table, but you simply will look up the degrees of freedom and the alpha value. So let's go and look at an example here. So if you're doing a Righttailed test, find the critical value for a sample of n equal 20 and an alpha value of 5%. So let's go look it up. So n equal 20 is right here, and it was an alpha value of 5%. So 0.25, so 25%, 10%, 5%, so third column. And degrees of freedom, so n was 20, so we need to go degrees of freedom minus 1, so we go to 19, and we get 1.729. So we would get 1.729, and that's because we did a Righttailed test, and our tables give the value to the right. So that's perfect. Let's do a Lefttailed test. So I'm going to challenge you to, well, no, I'll do this one with you guys. Although you should pause it and see if you get the same answer as me. So pause it, then come back and check. So for the critical value of n equal 15 and an alpha value of 2.5%. So for n equal 15, we go degrees of freedom. So there's 15, degrees of freedom minus 1, and it was 2.5%. So there's 5%, 0.025, and we get 2.145. So we get 2.145. But now it says the Lefttailed test, so it's negative 2.145. Okay. Now for a Twotailed test, find the critical value for n equal 32 and an alpha value of 1%. Okay, so we always go alpha divided by 2 for a Twotailed test. So instead of looking for 0.01, we'll be looking for 0.005 and an n of 32. Don't forget to do n minus 1. That doesn't look like an n. N minus 1, right, for the degrees of freedom. So we'll be looking for something as close to 31 as we can find. Oops. Now, you're going to notice when you look at your table here, once we get to n equal 30, it starts going up by tens. So we're looking for 31. Now, the closest we can get is 30, and we're looking for 0.005. So be careful. This is 5% here. 0.005 is all the way at the end. And we're looking for 30, so 2.750. So for the right-hand side, we would go 2.750. That's for the right-hand side. But for the left-hand side, it's going to be negative 2.750. So that's for the left. There. So now that you're an expert at finding your t-value, there's a quick little table here to summarize when you're going to reject HO. Right? If t is greater than t alpha for a right-tailed test, t less than negative t alpha for a left-tailed test, and then for the two-tail, you got to break it up into both. So you can review that table on your own. It's the same exact procedure for the z-scores, just slightly different because we're using a different table as far as the actual numbers we're going to get. Before I do this question, I do want to show you on our t-table, you won't use your z-table a whole lot more with this trick that I'm about to show you. So for the standard alpha values when you're doing hypothesis testing, okay, and you can only do this for hypothesis testing, I mentioned that there's this degrees of freedom infinity. So this means that your sample size has gone to like super duper super huge. Okay, so you see goes 30, 40, 60, 120, and then infinity. So infinity is a big number. When you take the degrees of freedom out to infinity for a t-table, you are now looking at a z-table. Okay, so if a t-distribution, if the sample size gets big enough, it just turns into a z-distribution, into the normal distribution, right? So this is a hack. You'll notice, like, if you look up 5%, and if you've been doing a lot of homework, you'll notice 1.645 is a critical value. That's the value that we've been looking up on the z-score table. So basically, you have all your common alpha values here: 5%, 2.5%, 1% are usually the ones we do, and then there's the two-tail, half of 1%. So if you look it up at infinity, you will be looking at the same value on your z distribution. You can confirm it, but believe me, it works. So huge life hack. It's a life hack. Okay. This one here, I think I got 2 examples here that we can do. So in this particular example, what do we got? Debt to equity ratio to limit risk in bank loans. Love banks. A large bank has decided to initiate a policy limiting the mean debt to equity ratio for its portfolio of commercial loans to being less than 1.5. So remember, ratio is when you divide 2 numbers together. Okay, so debt to equity. Take your debt, divide by your equity, and you don't want that ratio to be bigger than 1.5. Test the null hypothesis that HO is mu equal 1.5 versus the alternative that HA is mu less than 1.5. We're going to test at the 1% level of significance, and the data that we're given is n equal 15. The sample mean was 1.3433. Here's the sample standard deviation, and I went ahead and I actually wrote out the degrees of freedom, so n minus 1 is 14. Now, by the way, how would you know this is a t-distribution? Based on what's given? Well, 2 things. Number 1, if n is less than or equal to 30, then you're going to do a t-test. You also got to do a t-test if you don't know the population standard deviation and you have a small sample. So in this case, because you can see they're using S, so that's the sample standard deviation. Okay, you got small n, no population standard deviation, so I know that it's going to be a t-test. Okay, so let's go ahead and do it. Calculate the value of the t statistic. Yeah, sure, we can do that first. We already have our HO and our HA, so we don't need to do that. And remember, this is the formula that we're going to use, which is, basically the same as the Z one. And we can plug in our numbers. So we got 1.3433 minus 1.5, which is the number given in the question. And our standard deviation here is 0.1921 divided by square root of 15. Okay, now go type that in on your calculator, pause the video. You're going to get negative 3.1589. Now, we do need to go look up the actual t-score, right? So this is a left-tail test because we're doing mu less than 1.5. So remember, our n value with the degrees of freedom is 14, and we need to look up negative t 0.01. And we're going to reject HO if t is less than, let's go look it up. Come on. So if t, n equal 14, and we're looking for 0.01, so there it is, this column right here, 2.624. So negative 2.624. So we reject HO if our t statistic is less than negative 2.624. Now, we got a t value of negative 3.1589. Now, this is less than negative t of 0.01, which was equal to negative 2.624. So what do? We reject HO. Okay, so now this is actually a typo here. This should say 1%, so my mistake. So at the 1% significance level, What does it mean for us? It means that the mean equity to debt ratio of the bank's commercial loan portfolio is less than 1.5. There you go. Yeah, your first t-test. Now, I drew the pictures out over here. Now, remember, it's a good idea to draw the picture. It's not strictly required, but I always draw it to this day. So if you're kind of wondering if you're on the fence of whether or not you should do it, you should do it. All right. Let's look at a nice little example here. So it's a two-tailed t-test, and there's going to be more in your homework. So I'm just doing the two examples and in the notes today. So let's see. It's Halloween and Linda is doing some stats. Perfect. Linda feels she's getting a bad deal this year trick-or-treating. She wants to know if the mean number of pieces of candy she gets per house is different than last year. So that's the key metric there where you're like, different is usually a two-tailed test, right? Because I'm not saying it's greater than or it's less than. I'm saying it's different, which means not equal to. So it's different than last year. Last year, she got 3 pieces per house on average. This year, after visiting 30 houses, she figures she got 2 pieces per house with a standard deviation of 2 pieces. Test at the alpha equal 0.01 level of significance. So first question is, how do I know this is a t-test? Well, she clearly did an experiment, and we have her standard deviation, so it's the sample standard deviation. So we don't have the population one. Also, with n equal 30, that's just at the boundary there where it's not quite big enough to necessarily be normally distributed. So it's going to be a t-test. Perfect. So with all that established, we can go ahead and do our work. So I'm trying to lay this out in the way that you should do it. So what's your hypothesis? Well, she thinks, remember, do the HA first. She thinks that mu is different from last year. So it does not equal 3. Okay, that means that HO, if you look at your formula sheet for a two-tailed test, is going to be just mu equal 3. So status quo is 3. She thinks it's different. There we go. Let's go find the critical value. Now, remember, draw your picture. It's a two-tailed test. So we're going to reject HO in this region and reject HO in this region. We have an alpha value of 0.01. When you go alpha divided by 2, you're going to get 0.005. Okay? So we need to go look up. We had n equal 30. So degrees of freedom n minus 1, we're going to be looking up 29 at 0.005 for alpha. Okay, let's go look it up. So n is 29 and 0.005 is all the way at the end, so 2.756. So the critical value for T 0.005 for a two-tailed test with degrees of freedom 30 minus 1 is 29. We got 2.756. Now remember, on the right-hand side, it's positive here. This is T alpha divided by 2. On the left-hand side, negative T alpha divided by 2, so it'll be just negative 2.756. Okay, so you must write it. I kind of ran out of room, but you say right over here, if T is greater than 2.756 or T is less than negative 2.756, reject HO. Okay, so draw that picture and make sure you have that statement written there because it's your logic. Okay, that's your logical test that you're going to do. Now we're almost done. We just need to calculate the test statistic. Okay, so of course we're using this formula here, which I hope you're getting sick of writing and you almost have memorized. So plugging in the numbers, her x bar was 2, the mean, historical mean was 3, and standard deviation of 2 divided by square root 30. Go ahead, pause your video, plug that in a calculator, you get negative 2.74. Now, having the picture can really help because 2.74, I see that I'm just, was it negative? Yeah, I got negative, so I'm just over here. So it seems like I'm in the accept HO region. I can kind of visually confirm that. So you have to compare it. You got to write it out. So you can say since t equals negative 2.74 and whoops and no, it's doing that thing again. Oh, and negative 2.74 is greater than negative 2.756. We must accept HO. Then you have to write your conclusion. So at the 1% level, we do not have enough evidence to reject HO. So you say we cannot conclude the mean number of candies is different than 3. And there you have it. So, thanks for joining me, and I will post another video with some extra questions and things like that later in the week, and I will see you guys next time. Bye-bye.